Chemistry, the Central Science, Chapter 7, Periodic Properties of the Elements, Lesson 1. So first, let's just take a look at the development of the periodic table in terms of when elements were discovered. So we can look here and see that in the Middle Ages, right, platinum, zinc, phosphorus, arsenic, antimony, bismuth. Ancient times, so pre-Middle Ages, right, you have your iron, copper, silver, gold, a lot of your standard metals that we think about. And as times went on, of course, we discovered more group 1, group 2 metals. Our halogens were discovered, and then studying noble gases. These elements down here are extremely hard to isolate from each other based on their electron configurations, and trying to determine, do we really have a different lanthanide or a different actinide? Some major spectroscopic methods had to go in to study said things. And then, of course, we know that within the last couple years, these heavier elements here were discovered. So let's talk about effective nuclear charge, which is going to dictate things like how big an atom is, ionization energy, electron affinity, etc. So your effective nuclear charge is looking at a particular electron and determining how strong of the attraction does it have to the nucleus, right? Effective nuclear charge, then, you're looking at your protons, because Z stands for your atomic number, but as you start to get more electrons, the inner electrons will shield the outer electrons from feeling that full force of the nucleus. So your shielding effect comes into play when you have many electron atoms, and you start to have all these core electrons then that are basically blocking your outer electrons from feeling the charge of the nucleus. So for example, down here, we can look at what is our atomic number and then what is our effective nuclear charge. So we can see that there is a difference from the atomic number and what those electrons actually feel. There are different ways that ZF can be calculated, and we'll take a look at that in the book. So atomic radii, how can we figure out how big an atom is, right? Its size. So in metals, for example, like copper, copper's only bonded to copper. So doing X-ray crystallography, you can measure the distance between two atoms. Same thing in studying molecular compounds, F2, O2, N2, right? If we are able to look at what is the bond distance there, we cut it in half and say, well, then that must be the radius of each of our respective atoms. So what are our trends as we look at our periodic table in terms of atomic radius? Well, as you go from right to left and top to bottom, we see that we increase in size. Conversely, right, as you go from bottom to top and left to right, we get smaller. So we're getting bigger as we move down the periodic table because each row represents a new energy level, a new principal quantum number, which says now this is our distance from the nucleus that our next electrons are going to fill in terms of that shell. So that's why we get bigger as we go top to bottom. As we go left to right, we get smaller because we are adding electrons to the same shell. Each time you add an electron, you're also adding a proton. Protons are 1,000 times bigger in mass than what an electron is. And so as we add successively more protons, our atoms actually shrink because then their effective nuclear charge increases. So as we go from left to right, the effective nuclear charge increases, which is why our atoms get smaller. As we go from top to bottom, our atoms get bigger because we're starting to add electrons to a new energy level, which is a farther distance from the nucleus. So smallest atom is helium, largest is cesium. Here's just another way to look at some trends in atomic radii. So it's just showing as we go across our rows, we do indeed see that our atoms are getting smaller. Of course, transition metals do weird things based on the fact that they're filling in their d orbitals with those extra electrons. So now we can look at cations and anions in terms of their sizes. So when a cation is formed, it is losing an electron. Therefore, it's going to shrink because our effective nuclear charge goes up. So lithium to lithium plus, we can see that it got smaller. When an anion is formed, it is accepting electrons. Therefore, its effective nuclear charge is smaller on those electrons that are added. Therefore, we see an increase in size, so fluorine to fluoride. We can also think about this in terms of, well, we have more electrons. They repel each other, so they're going to want to spread out. So the more electrons that we lose, the smaller we get. The more electrons that we gain, the bigger we get. So we can look at, once again, these are just general trends of what sizes are. So for our cations, we still see that they're, well, for both cations and ions, we can see that the trend is still true, that from top to bottom we get bigger because, once again, we're looking at that principal quantum number increasing. So regardless, you're looking at electrons from further away. So top to bottom, we get bigger. As we become more positive, let's just look at sodium, magnesium, and aluminum. So across group row 3. So +1, +2, +3, we've lost more electrons. Therefore, we are smaller here than what we are over here. So that is true for all cations. The more electrons you lose, the smaller you get. So that is our trend in terms of looking at cations. Looking at anions, we still have, as I stated earlier, our trend of getting bigger when we go from top to bottom, and then we are also shrinking as we go from left to right. Why? Well, if we look here, nitrogen accepted 3, oxygen accepted 2, fluorine only accepted 1. We think about the number of protons that we have. Our effective nuclear charge is stronger here than what it is here. So we're still continuing to shrink as we go from left to right. But of course, once we hit our nonmetals that become anions, we see a great increase in their size. So comparing atomic radii to ionic radii, looking at our group 1 metals, we see their atomic radius compared to their ionic radius. So clearly we're getting smaller. Over here, we look at our halogens. We notice that as we accept electrons, we get bigger. So in terms of classification of our elements, we're always looking at what are our valence electrons, because those are the electrons that participate in reactions. So your valence electrons are those that are farthest away from the nucleus. They're the largest distance away from the nucleus. They're in the highest energy level. So your core electrons then are all those other electrons that are in your shells and subshells that are closer to the nucleus. So when we talk about isoelectronic, we're talking about elements that have the same electron configuration or the same number of electrons. So for example, when sodium loses an electron, it has the noble gas configuration of neon. Aluminum and fluorine will do the same. Aluminum loses 3, it starts with 13, so now it has 10. Fluorine starts with 9, it accepts 1, so now it has 10. Oxygen accepts 2, it had 8, now it has 10. Nitrogen accepts 3, it started with 7, so it has 10. So all of these atoms are considered to be isoelectronic. Na+, Al3+, F-, O2-, N3-, and neon are isoelectronic, iso meaning the same. So ionization energy is the energy that has to be put in to remove an electron. So this energy then is endothermic. It has a positive value. You have to overcome the electrostatic force between the nucleus and the electron that you want to remove. So the way to break these down, and electrons can only be removed one at a time. This stands for our first ionization energy. So we take a neutral atom, we take away an electron, it becomes a +1. Your second ionization energy is then looking at the cation you just formed and removing another electron to become a +2. We can continue to go. The third ionization energy, well, we've taken away 2 electrons, let's take away another one so that we end up with a +3 charge. And we can continue to do this, 4th ionization energy, 5th ionization energy, etc. But these are how the equations will always look. You start with something as your reactant. On your product side, you are increasing the charge by 1 because you are losing an electron. So all ionization energy reaction equations have this type of setup. And as you successively remove electrons, it gets harder and harder to do that. Why? Well, as we're removing electrons, our effective nuclear charge is increasing because we have less electrons there to hold on to. And because our atom is shrinking, right? So it's like, hey, I want to hold on to the rest of my electrons as much as I can. You've already taken one away. So here's a variation table on the variation of the first ionization energy with atomic number. So as we can see, our highest values for ionization energy in a specific row or period are going to be your noble gases. Why is it the hardest to take an electron away from a noble gas? 1, it has the highest effective nuclear charge in that row. 2, it's going to be the smallest of all of those atoms in that row. 3, the noble gases are stable. They don't want to lose electrons. They don't want to gain electrons. So it's really hard to take electrons from them. So then what's the other trend that we notice? Well, as we go across our rows, so lithium to neon, we see that it's easier to take an electron from lithium than what it would be from fluorine. Why? Lithium has 1 valence electron. If you take it away, it has a noble gas configuration, so it's more stable. We know that metals like to lose electrons. So our group 1 metals are the easiest metals to take electrons away from. And then as we move across the periodic table, it gets harder and harder to take electrons because we know nonmetals don't want to give up electrons. They want to gain them to become more stable. So in looking, and as I said earlier, our noble gases, right, have completely filled shells. So that's why they're the most stable, and that's why they don't want to lose electrons. So what's our general trend here that we can look at? Well, as we go from top to bottom, our ionization energy decreases. As we go from right to left, our ionization energy decreases. So cesium has the lowest first ionization energy, and helium has the largest. So this is just the opposite trend that we saw for atomic radius. So what does this mean? Well, if helium is the smallest, it's also the hardest to take the electrons away because it has the highest effective nuclear charge. If cesium is the largest, it has the lowest effective nuclear charge, so it's easier to take an electron away, right? And with your group 1 metals, all you have to do is take one away. And when you have a whole bunch, it really doesn't matter because the effective nuclear charge on that outermost electron is so small, it's just so much easier to remove it. So we can write electron configurations of representative elements as their ions. We looked at this earlier in terms of how are we taking electrons away. So noble gas configuration of sodium, right? We have a neon 3s1. So we take that 1 electron away and now it becomes neon. Calcium has a total of 20 electrons. So argon has 18. We then have a 4s2. If we take those 2 electrons away, we end up with the calcium 2+ and a noble gas configuration that is isoelectronic, right, with argon. We can do the same thing for aluminum, noting that aluminum wants to have 3 electrons removed from the 3s2, 3p1, right? These are valence electrons because they are the furthest away. We end up with aluminum 3+. Noble gas configuration is neon. So your atoms are always going to lose electrons from your s and your p orbitals in terms of our main group elements. That's how we go. We go from an s orbital, and then if we need to take more, we take from the p orbital. So if we're adding electrons, right, if hydrogen becomes the hydride ion, we go from a 1s1 to a 1s2, which becomes the electron configuration of helium. Now keep in mind when we're talking about this, we're not saying that sodium plus is the same as neon. It's not. It's just isoelectronic. It has the same number of electrons, but we're not turning an atom into a new atom. So fluorine starts with 9 electrons. We're going to add that electron to the last empty p orbital there so that we get 10 electrons, which is the same electron configuration as neon. Oxygen starts with 8 electrons. Our 1s2, those would be considered our core electrons. And the 2s2, 2p4, that tells us that oxygen has a total of 6 valence electrons. So we accept 2 electrons and then end up isoelectronic with neon. Nitrogen will do the same thing. Once again, if we look at the second energy level there, it shows us that nitrogen has 5 outermost electrons, valence. To get to 8, it accepts 3, and then it has the same configuration as neon. So your atoms are going to gain electrons into their p or s subshells. So when we're looking here, as far as nonmetals go, they're always going to accept into their p orbitals because their s orbitals are already filled. So transition metals, we know, do different things. So when we form a cation from a transition metal, electrons are always removed first from the s orbitals because they are the furthest away. Then we start to remove electrons from the d orbitals. So it's always your s orbital because the s is higher in energy. When you write your electron configurations, you'll see that. So the noble gas configuration for iron is argon 4s2 3d6. So Fe2 plus, then we're looking at taking away those 2 electrons from the s orbital. So we end up with argon 3d6. If we become Fe3 plus, then we note that we've taken an electron from the d orbital as well. And now if we were to write out a orbital filling diagram, we would see that in the d orbital, we have 5 orbitals, or I should say d subshell. We have 5 orbitals then that each have a single electron and they're all spinning the same way, right? So 5 unpaired electrons for the iron 3 plus makes it extremely stable. We can look at the same thing for manganese. So manganese first will lose 2 electrons from the s orbital, making it extremely stable because it would have the same electron configuration as iron 3 plus, leaving those 5 electrons alone in the d orbital. And then, if manganese wants to become a 3 plus, we of course know that it would take another electron from the d orbital. So we keep taking electrons from the d orbitals because really the d subshells are kind of buried within the atom of where they store those extra electrons.